Let's look at the arrays and vectors that we already have built or will be building in the future. First of all, we've got dict, D-I-C-T, the global array dict. It's indexed by words or terms. For the most part, these are going to be stems, but in later phases, we'll use other things. It's the vocabulary. This is the vocabulary we're using for indexing. These are the words we've kept. These do not include the stop list words, things like that. The value at each element of dict is the total number of times the term occurs in the collection. The next one is DF, or document frequency. It's also indexed by word. It's also a dictionary. The words are the collection. The words are actually terms. They've been stemmed. In some cases, there'll be other things, as we'll see later. This is a vector which gives us the total number of documents each word occurs in. So if I have some word, medicine, and it occurs in dict 100 times, that means it occurs 100 times in the collection. In DF, it might occur 25 times. Well, that means it occurs in 25 documents. So on average, it's occurring about 4 times per document. So one is the total number of times the word occurs in the collection. The other one is the total number of documents the word occurs in. The next one is IDF. That's also indexed by word. This is the inverse document frequency weight. We'll be calculating it soon. It's a very simple weight to occur. It's the weight of the word in the collection as a whole. We use this in conjunction with the rate at which a word occurs in a document in order to come up with a weight for the word in the document. At the IDF level, it's the importance of the term in the collection. But in an individual document, that word may be more or less important. The MCA vector is the modified centroid algorithm results of term weighting for a word. The word or term is the same as in the others, and the MCA value that's stored here is also a weight of the term in the collection as a whole. It's also known as the discrimination coefficient. It's much more expensive to calculate than the IDF, and its results are not materially better in many cases. However, we'll look at it. There are some other weighting schemes, but these are the only two we'll basically look at. The next one is the document term matrix. The basic document term matrix consists of the document number and the word. So the document number is the row, and going across the row are the words. At each position for a given document number and a given word, we will store initially the number of times the word occurs in the document. We've already done that when we created the document term matrix. In later steps of this project, the value stored here will be the weight of the term in the document. We'll have to calculate that. Initially, it's simply a count. Later on, it's a weight. The third item here is the position of the word in the document. For each instance of a word in the document, we'll have a position of where the word occurred in the document. And that is relative to 0. It'll be a count. So we use that in order to determine word similarities or word relationships. If two words occur close together and in the same order frequently, that probably indicates that they are related in some fashion. If they occur randomly before and after and a considerable distance to one another, even if they co-occur frequently, there's probably not much of a relationship between them. So this position indicator here tells us where each word occurred. So if a word like medicine is in a document 5 times, there'll be 5 values of POS telling exactly where it occurred. For most calculations, we're only going to use the first 2 indices, document number and word. This position will only be used for calculating similarities. The next one is the index array. It's the transpose of the document term array. The rows are words and the documents are columns. And the value stored here is the same as in the document term matrix. It is simply the transpose, nothing more. So if I have a word, I can find all the documents in which the word occurred. And I will also have the weight of each word in each document. It's more for retrieval purposes. The next one is the DD matrix. It is the document matrix. It tells us the similarity between any 2 documents. So it's a square matrix. Say I have 1,000 documents in the collection. It's 1,000 by 1,000. The diagonal is meaningless. So if I have document 1 and document 2 where they are different documents, say document 10 and document 20, the value stored at that location in the matrix is the similarity of those two documents, as calculated by some algorithms we'll look at later. That similarity is a threshold. We don't calculate, well, we do calculate the similarity of most of them, but it has to exceed a certain threshold value in order to be stored here. Otherwise, the matrix would become impossibly large. The values that aren't stored, of course, in mumps don't exist. The value here can be used, of course, if I've got a document, I can find similar documents to it relatively quickly. Next one is the term-term matrix. It's again like the document. It gives us the similarity between two terms in the collection. It's also a square matrix. It is also thresholded. Words will randomly occur at a certain level, but they have to co-occur or be similar above a certain threshold in order to make it into this matrix. Again, this is used in order to calculate similarities, and we'll look at that later. We've already seen the title vector. For a given document number, it gives us a title. It's truncated at a certain length, but it's the title, so when we do retrieval and we want to print out the titles of the documents, we can get access to them quickly. Remember the document term matrix up here. Document term matrix at up arrow doc sub D, that's where I close it off right there. What's stored there is the offset in the original file of where the records for the original abstract are located. So I don't really need the title. I could go back in when I do retrieval. I could go back in to the original file and extract the title, but it is quicker and easier if I have a separate vector of titles. So it's document number, and they are possibly truncated. They don't keep the entire title. We don't want a lot of runoff and so forth. The TTP is basically the term matrix, but it has an additional level beneath it, which gives us the summation of the proximity information. So if I have some word A and some word B stored at the third level, which always has this constant 1, will be the score of the proximity calculation. Do they occur frequently close together, and do they occur in the same order frequently? So that information is stored. There's only ever one level deeper. There will be some other vectors and matrices, which we'll see when we get down to them, especially related to term-term correlations. This is a list of the principal output files. Most of the steps result in a text file, which gives an overview of what happened. These files are not terribly legible in many cases. They're quite large, but here they are. There's deleted words and docs for IDF.txt. What that is, I think they're all .text. What that is a file consisting of the words that were deleted because their IDF score, inverse document frequency score, was too low. When we calculate the IDF for each word, it'll be a range of values, and we'll pick a cutoff. And words that are below that cutoff we'll delete. It's again somewhat similar to doing stop lists. But if a word is insignificant in the collection as a whole, we probably don't want to keep it. Some words, for example, in the medical collection, the word medical and medicine is in there everywhere. It's a very low importance term, and it'll show up as such. Deleted words for frequency, words whose frequency was too high or too low. There'll be a list of them. Discrimination coefficients .text. This will be a list of words and their discrimination coefficients, just a printout. Document clusters by title. We calculate clusters of documents in later stages, and these will be the clusters, and it'll be the titles of the documents in a cluster. So it'll be cluster 22, and there'll be there'll be the titles of the documents that are in cluster 22. So the purpose of that, of course, is we can look at the cluster titles and see if they do appear to be somewhat similar to one another. There's actually document clusters text. This will be the document numbers and the titles of the documents in a cluster. It's similar to the above. There's the document term matrix, document matrix, excuse me. This will be for each document, all the other documents that it's related to, and the degree to which it's related. There'll be a score from 0 to 1. Well, 0 won't be there because we have a threshold below a certain value. We won't calculate it. The documents have to have something in common, so there'll be a large number of documents for which we will not calculate a document value simply because they have no terms in common. Then once we do calculate it, we'll look at the value, and if it's too low, we won't store it. The document term matrix weighted. This is, again, the document term matrix, but we'll see it weighted by whatever scoring system we're using, either IDF or MCA or discrimination coefficient. I say MCA a lot. It's discrimination coefficient. MCA is a technique to calculate a discrimination coefficient. Discrimination coefficients can be extremely expensive to calculate. And some people a number of years ago came up with speed-up techniques. They do dramatically speed up the calculation, but it's still very expensive. IDF weights sorted. This will be a list of terms and their IDF weights, inverse document frequency, and it'll be sorted by inverse document frequency. So you can see the most important words and the least important words. The very rare words that only occur a small number of times tend to be listed as the most important, and the most common words are the least important. Term clusters, we cluster terms. We look for words that are related with one another, not just one word related with a second word, but words that seem to be forming a cluster. They're all related to one another in some fashion. The document term matrix weighted, that is the term document matrix. Excuse me, I read that wrong. It's similar, same as the one up above, really, but it's the transpose. The term document matrix is the transpose of the document term matrix. So this gives us by term the documents. So we can look at there. So we're given term, we can see which documents contain that term and to what and the importance of the term in the document. Term frequencies. A list of words along with the number of documents in which each occurs. That's the DF vector, basically. Term-term cohesion similarities. This is another term-term calculation. We'll look at it later. It's a calculation Salton came up with called cohesion. There's a term-term Jacquard similarities using a Jacquard calculation of similarity of terms. The term-term matrix sorted, and it's sorted by term. Term-term proximity similarities. These are the similarities between two terms based on their proximity. And finally, a term text, if we can calculate it. Basically, if term A is related to term B and term B is related to term C, we could make the conclusion that A is related to C, and that's what that attempts to do.